Hey there. Welcome to lab number 3, where we're going to be talking about atomic spectroscopy. We're going to be looking at the energy levels within the atom through this technique. So let's get started, shall we? First thing we need to really talk about is something called electromagnetic radiation. We abbreviate that EMR. Now, electromagnetic radiation has a lot of similarities between one band and the other, and some differences. So let's talk about those. First of all, electromagnetic radiation is really simply packets of energy. And we'll talk more about those in a second. We call these little packets the photons. Photons are simply packets of energy that can be transmitted from one place to the other. Now, there are different types of these photons listed in this chart. For example, we have gamma rays, which are very high energy photons. A little lower energy than that, we have X-rays. We're all familiar with ultraviolet radiation. And there's a narrow band of electromagnetic radiation that we call visible light. So our biology has developed so that we are able to detect this particular type of electromagnetic radiation with our little peepers. And it will actually separate that out in our brain for us as different energies being perceived as different colors. So we can have red light, orange, yellow, green, blue, indigo, and violet. Roy G. Biv, backwards in this case, as the different types of visible photons. And again, this is kind of in an energy, descending energy as we go across. We also have infrared radiation, radar, FM and TV, shortwaves, and AM radio is the lowest energy in that particular spectrum. So let's talk about wave mechanics a little bit. Now, let's talk about a different wave mechanic. Thanks, Ralph. When we think about waves, there's a few things we need to understand about a wave. And we do this because there's a duality of nature with this photon. It does behave as a wave, and it does behave as a particle. So when we're talking about it in this particular subject, we're really going to be focusing on its wave nature. So when I'm looking at a wave, how can I quantify aspects of this wave? Well, first of all, there's something called the wavelength. And the wavelength is simply the distance from one wave crest to the next, perhaps from this point to this point, or it could be from one trough to the next. The distance between those points is the wavelength, usually in meters, centimeters, nanometers, depending on the type of wave. There's also something called the frequency. How many waves are being produced per second? So in this particular case, it looks like there's a little less than 1 wave per second being created. Now, if I'm making 5 waves per second, I would say that the frequency is 5 hertz, meaning 5 waves per second, abbreviated capital H, small z, hertz. If there's 20 waves being formed per second, it's 20 hertz. Simple. Something we really don't talk about in this lecture, but you should know for wave mechanics, is the height of the wave from its baseline is what we call the amplitude. And one of the other things that will come up is the energy of the wave is really proportional to its frequency. So let's talk about the photon. It is a light quantum. It's a little packet, a very discrete amount of energy. And that energy is transmitted as electromagnetic radiation. And as I mentioned, it has a dual nature as this packet, but also as a wave. Now, some formulas that we're going to have to deal with here is that for any wave, its speed is simply its frequency times its wavelength. So if I'm making 3 waves per second and they're 5 meters apart, 3 waves per second at 5 meters apart would be a velocity of 15 meters per second. For electromagnetic radiation, all of them move at the same rate. We call this c, 3.00 times 10 to the 8th meters per second. C is the speed of light. Why? Electromagnetic radiation is light. Well, it's also X-rays, it's also radar waves, microwaves, etc. But they are all the same thing with different packets of energy amount. The packets have different amounts of energy. So we end up with this formula. The speed of light equals the frequency times the wavelength, where the speed of light is always going to be 3.00 times 10 to the 8th meters per second. So given the frequency, I can find wavelength. Given the wavelength, I can find frequency because I know the velocity. There was a guy named Max Planck who figured out that if we were to graph the energy as a function of the frequency, that there would be a linear relationship. And of course, as a math student, you're asking yourself, what is the slope of this line? And it turns out the slope is equivalent to 6.6 times 10 to the negative 34th. Our energy is in joules, our frequency is in hertz, so our slope would be joules over hertz, rise over run. The slope of the line being 6.6 times 10 to the negative 34th. So there's a direct proportionality between the frequency and the energy. Therefore, we have this equation. The change in energy is equal to Planck's constant, 6.6 times 10 to the negative 34th, times whatever frequency we have for that particular photon. And again, Planck's constant is a constant, so anytime I know the frequency, I can directly convert that into the change in energy for that system. Next quick point. We have talked about electron configurations where the electrons are at the lowest possible energy level. It is possible for those electrons to hop up into higher energy states. We call those excited states. For example, if I had helium with 1s 2 electron configuration, but one of the electrons hopped up to the 2s, that would be an excited state. Why? Because the 1s isn't full. An electron has moved up to the 2s. Now, when an excited state electron returns back down to ground state, or at least a closer to ground state, there's a loss of energy. It's gone from higher energy to lower energy. Where does that energy go? It is released as a photon. So the photon energy is really related to the energy difference between one energy level in the atom and another. We can see that in this diagram that the energy emitted is really Planck's constant times the frequency of that particular photon. That would be equivalent to the energy change from one level to the next, simplified in this Bohr model. But let's talk about how photons could be produced. What are our possible scenarios here? Well, let's pretend we have a hydrogen with a single electron, and we live in a world where there's only four different energy levels, four principal energy levels. What are the possible motions for this electron going from an excited state to a less excited state or ground state? Well, let's kick this electron up into the fourth energy level. Now it's in the excited state. Where can it go? Well, it could fall back to the third energy level. It could fall back to the third energy level. It could fall back to the second energy level, or it could fall back to the first energy level. So which one of those represents the greatest change? Well, obviously going from 4 down to 1 is the greatest change. When you think about the photons being produced as a function of their energy, the higher the energy jumps create a higher frequency photon. Think about making a wave. If I have a rope attached to the wall there, and I really start shaking that with a lot of energy, the frequency has to go up. If it's a low energy wave, then the frequency is low. So obviously this biggest jump is going to produce photons of a higher frequency. Yes, that does mean shorter wavelength. This little tiny jump from 4 to 3, these photons are going to have a longer wavelength, a lower frequency. Okay? And this guy in the middle, somewhere in between. Now, what other possibilities were there? We could have had the electron going from 3 to 2, or 3 to 1. And again, that would be two different flavors of photon, different energies. And there would be a situation where the electron could jump from 2 down to 1, creating another photon with a different frequency. Now, in this world I've created, there are actually 1, 2, 3, 4, 5, 6 different types of photons that could be produced. Now, an electron can't go from 1.5 to 2. It can't go from 3.6 down to 1.4. It can only go from 4 to 3, 4 to 2, 4 to 1, 3 to 2, 3 to 1, 2 to 1. Those are the only possible jumps. Therefore, this atom is only capable of producing 6 different types of photons of different energy. So how could we determine what those energies are? Well, let's go back to our little continuous spectrum of visible light. You'll notice that the different colors are associated with different wavelengths. Therefore, because the speed of light is constant, these would have to travel at a different frequency, thus having different energies. These guys up here would be higher energy, and the ones on the right would be of lower energy. So when we go back to our previous example, this big jump from 4 down to 1 might represent perhaps a violet photon, whereas this little tiny jump up here may be so small that it's actually in the infrared part of the spectrum, not even visible, too low of energy. Well, maybe this jump from 3 to 2 would fall in the red part of the spectrum, but this jump over here might fall in the yellow part of the spectrum. My point being, there's only certain photons that can be produced. Therefore, we're only going to see certain regions of the spectrum highlighted. For example, there might be photons produced in this region to correspond with one specific jump. We said one of them might be there in the infrared part of the spectrum, but we had 6 different photons, and perhaps they coincided with those different colors. That element can only produce those 6 types of photons. There's not any other element that will do the exact same thing. So this is unique to each individual element based on the arrangement of its electrons and the distance between the energy levels. This is actually how helium was discovered, by the way. When they were looking at different atoms and the pattern of photons they can produce, they noticed the sun was producing a pattern they had never seen before on the Earth. They named that element helium, because of Helios being the sun. So here are some examples. When we're looking at sodium, so if we take some sodium and we add energy to those sodium atoms through heat, maybe zapping with electricity is a common way to do it, we can get those electrons to start hopping around within the atoms, and then we start to see these patterns forming. Really important in astronomy, too, this particular subject, because we can look at the starlight and look at this pattern of light and figure out what elements are in that particular star. Sodium always shows these 2 lines right here, a set of 3 here, 2 here, and 1 here. Now hydrogen shows 2 in the bluish purple, 1 in the yellow, 1 in the red, and magnesium, a whole different pattern. So this is indicative of, again, where the energy levels are within that atom and where the electrons can jump to and from, again, producing a photon each time it moves from a higher energy to a lower energy, going from a higher excited state to a lower excited state or back to ground state, emitting a photon that coincides with a specific color. So what we can do is excite an atom, again, by subjecting it to an external source of energy, and cause its electrons to hop from one level to the next. So over here on the right, I'm creating an atom, my own atom. Energy level 1 is here, 2 is here, I'll put energy level 3 here, 4 here, 5 here, and 6 here. Now I'm going to fire electrons into this particular atom, and you'll see in the visual that the electrons are hopping up and then falling back down, emitting photons. So over here on the right, you can see the position of the electron, going from 6 down to 3, from 3 down to 1. And you'll also notice that photons are being given off of different types. Now, how do I know what the photons look like? What kind of photons are there? Well, we can separate out all the different colors through the use of a prism-like device. Not a prism, but a prism, to separate all the colors. We call this a spectrometer. So let me turn my spectrometer on, and let's see what kind of photons are being produced. So each of the photons is being passed through this spectrometer, so they're being separated out by their colors. So we can see that we're getting some purple photons, some blue photons, a bunch of yellows, and some red. Some are falling down in the infrared part of the spectrum, so we wouldn't see those. There's some in the ultraviolet part of the spectrum for big jumps, and we wouldn't see those obviously. But this color pattern is indicative of the distances between the levels. So what happens if I change those levels around? Well, let's take a look. There now I've created different distances between the energy levels. That may happen because I have different numbers of electrons in the atom, which causes the energy levels to space out differently. So any different atom would have a different distribution of its energy levels. Let's see what the spectrum looks like in this situation. And now we see a different pattern of our spectral lines due to the fact that the energy levels have changed. So every atom has its own unique spectral pattern. This is called the emission spectrum because it's the photons that can be emitted by that particular element. It also works with molecules, but each set of electrons has specific jumps it can make. Therefore, certain spectral lines will show up in the spectrograph. So as we noted, the spectrometer is going to allow us to measure the wavelengths of those particular photons. Once we know that wavelength, we can use the formulas that we were introduced to actually calculate the energy of those photons, thus figure out the distance between the energy levels within that atom. Let's take a look here. What is the energy of a photon with a wavelength of 4.10 nanometers? Nano means 10 to the negative 9th. If I were to take this thing and put it into scientific notation, I would know that my wavelength is equal to 4.10 times 10 to the negative 7th meters. I'm sliding my decimal place over twice there. We can use the formula, the speed of light is frequency times wavelength, to solve for our frequency. So our frequency must equal speed of light divided by our wavelength. Speed of light is always 3.00 times 10 to the 8th meters per second. We divide that by our wavelength, and we're going to get a frequency of 7.32 times 10 to the 14th hertz. Again, that's the number of cycles per second. Now we're going to find the energy by using energy equals Planck's constant times the frequency, where Planck's constant was given as 6.6 times 10 to the negative 34th joules per hertz. So we multiply that by the frequency we found in the previous calculation. Good thing we know how to work in scientific notation. And we come up with 4.83 times 10 to the negative 19th joules. Extremely small amount of energy, but you got to remember, this is a single photon, which was produced by a single electron, moving from one energy level to the next within a single atom. We're talking about a very small scale here. Thus, we're getting a small scale of energy. That is the energy of a photon with a wavelength of 410 nanometers. What we're going to do now is we're going to look at hydrogen, and we're going to figure out what is the energy level differences within the hydrogen atom by looking at its spectra and doing the calculations, very similar to what we just did in this example. So let's take a look at our simulated hydrogen atom, showing 6 different levels for the electron movement. And we're seeing 4 different spectral lines in the visible part of the spectrum. There's a few out here in the infrared and a few in the ultraviolet as well. We're going to concentrate on the visible ones. So I see a violet line happening at about 412, a blue happening at 436, this light blue at 485, and this red happening about 657 nanometers. So we're going to take this information and transfer it over to our labs, as I'll show you in a second. So I've taken the information from our spectrometer. I've moved my wavelength into meters from nanometers. Nano again is 10 to the negative 9th, but when I'm sliding the decimal 2 times over, it becomes 10 to the negative 7th. So now that I have this in meters, we can calculate the frequency of each of those photons. And once we have that, we can calculate the energy of the photons, again using the information that energy is frequency times Planck's constant, and the speed of light is frequency times wavelength. We have our Planck's constant value and our speed of light value there, allowing us to accomplish this. So now what I'd like you guys to do is go ahead, perform these calculations so we know the energy of the photons being produced. Thus we'll know the energy differences within our hydrogen atom. We've essentially dissected our hydrogen. Once you've completed that, could you go ahead and answer the 5 questions for this lab with your group, and I will see you back in class. Thank you.